Okay, welcome back to lecture number 3. And this is my favorite part because it's about relationships. And I love the stories that we can tell about statistics of different data sets and the relationships between those statistics. I also get a kick out of this because of the way that people tend to think of this and the mistakes that they make that paint some pretty silly pictures. So we're going to have some fun with this. When we have just one data set, it's called univariate. There's no way to show relationships within one data set or with one variable. But as soon as we get two variables and we go to bivariate, we can start to describe the relationship between those two variables. So things like height and weight, they generally go together. Age and reading level, there's usually a relationship there. And when there's not, we actually start to get a little concerned. This is important information. Other relationship, years of income level, years of education and income level, you can find a pattern there. Definite relationship somehow between math aptitude and math achievement. All kinds of things that we want to describe the relationships of and can find some really interesting stories in our data sets. The two tools that we use and you need to be familiar with for understanding the relationships between variables are scatter plots and correlation coefficients. So let me talk first about correlation. Correlation simply means that there's a pattern. As one variable changes or the score is different than the other one, you'd expect the score to be different also. So taller is usually associated with a heavier weight, shorter with a lighter. And I've put two charts here. They have exactly the same information in them. In the one on the left, we measured the height and the weight. So you can see that they start down under 40 inches tall, and the weight is probably about maybe 25 or 30 pounds. And then as we measure people and they're taller and taller, their weight generally goes up. It's never perfect, or we would be measuring exactly the same thing. Now in the left, I reversed them. I simply put the height on the left and the weight on across the x-axis. Now, we need to be really careful when we're talking about statistical analyses and we get into inferential statistics. A lot of textbooks and professors make a big deal that you've got to never equate correlation with causal. And yet that's kind of counterintuitive. For example, weight doesn't usually contribute to your height. If it did, my son would have tried to gain a lot more weight so he could be taller like his uncles. It just doesn't make sense. But height does seem to contribute to the weight. You would expect that your height does affect your weight. It's pretty hard for pretty hard to imagine someone who's 6 feet tall and only weighs 75 pounds. That's ridiculous. There's obviously some kind of relationship there, but we have to be careful that we don't call it causal. And I think that what people get hung up on is saying that your height causes your weight. Well, it doesn't. It contributes to your weight. It's one of the factors that contributes to weight. So don't get hung up on the causal, not causal. Often when we correlate two variables, one precedes the other in time. And so if that happens, or the one that seems to be a factor in the other one, we usually put that across the x-axis, which is the horizontal axis. So you have to be careful with relationships and correlation, that you don't go saying this caused that, and because people will call you on that one. We represent the relationship between variables with a number between 0 which means absolutely no relationship, and 1, which means you're basically measuring the same thing. There is a perfect correlation there, or a perfect relationship going on there. And we also give it a sign, and that indicates the direction of the relationship. So a correlation coefficient between 0 and 1 is given a plus or a minus, and that gives you the strength of the relationship, or the magnitude of the relationship, and the direction. So let me explain a little bit more about that. 0 means that statistically there is absolutely no relationship between those two variables. So some examples of this would be the length of your nose and your marital happiness, or the size of your index finger and your intelligence. There, you're going to find no relationship there statistically. That doesn't mean there's not a relationship. It means that by using the numbers, we can't find a relationship, and so we give it a 0. 1 means there's a perfect relationship. Those variables go together so well that you can't even distinguish them. And that's the problem when you get a relationship that's that strong with a magnitude of 1. You may be measuring the same thing 2 different ways. So if I am trying to show the correlation or the relationship between math aptitude and attitude towards math, aptitude, attitude, and I end up with a relationship of 1, I don't even need both measures. I'm measuring something that's so close to the same thing that I can't distinguish it. For general rules of thumb, and these are just general, in educational settings, we tend to be real happy even if we get lower relationships than we thought we would. So, but less than 0.35, either positive or negative, is pretty low. There's a weak relationship there. There's something going on, but not very strong. In the middle there, you can see what I've suggested is a moderate correlation. And when we get up towards the upper end of these moderate correlations in educational research, we're still pretty happy. We've found something there. If you get above a 0.66, you've got a pretty strong relationship going there between those two variables. Something is happening together. Now, when we're looking at the correlation coefficient, we're actually looking at the slope of a line and how steep it is. So if I line up all these scores, and those are the blue dots, and then I put in a line that goes through the middle as close as I could come to touching all of those dots, you can see how steep that line is. And the left graph, the correlation coefficient is 0.98. We indicate it with a small r. That shows you your correlation coefficient. So the correlation in this line is almost 1. It's a very, very steep line. Over in the middle one, if I draw a line trying to get as close as I can to touching all of those dots, you can see that the line is not as steep. The slope, as the x-axis is changing, the y-axis isn't changing as much. And let me say something here about change. We tend to use phrases like that. As the x changes, the y changes. The score, the blue dot that represents 1 on the x-axis, and is that a 5 on the y-axis, that score is not going to change. That is the score. It's not the score that changes. What we're talking about, the change, is moving over to the next score, which looks like it's 1.5, and it's down at what? A little over 4. That's what we're talking about, a change, is the difference in the scores. Not that this first person's score changes and so the y score changes. We're talking about the difference as you move across the x-axis. Now look at the right graph. If I try to draw a line as best I can, the closest I could come with a straight line to being as close to those blue dots as I can that represent all the scores, it's really hard to do, for one thing, and it's a very it's not a very steep line at all on the slope. There's not much of a relationship going on there with those. Actually, the correlation coefficient is 0.32. Now here's what I mean by direction. On the left would be an example of, as height increases, the weight increases. So as I move from the left across the x-axis, as those numbers get larger, going up the height on the y-axis, they would also get higher. They would get larger. So that's what we call a positive correlation. On the right would be an example of, as the numbers get higher along the x-axis, they get lower on the y-axis. So an example of this would be as children get older, maybe you've got some little ones, as children get older, their childcare costs, what you pay for babysitters, decreases. I don't know if that's a real example, but it just popped to mind. So a 1-year-old, what is that, a 3-year-old, a 4-year-old, a 5-year-old? Ooh, that's a great scale across there, evenly spaced out and everything. But so by time a child is in school, the costs for the child care each day are going down as the child gets older. So that's a negative correlation. It doesn't mean good and bad. In that case, I would think the negative correlation would kind of be a celebration in the family budget, because as the child gets older, it's costing less for the babysitter. So it's not a good, bad kind of thing. Positive simply means that as the x-axis numbers are getting larger, so are the y-axis. And negative means that as the x-axis numbers are getting lower, the y-axis or x-axis numbers are getting larger, the y-axis numbers are getting lower. That means negative. Now, one way to look at whether there's even a correlation or a relationship there is to draw kind of an oval or a circle around the dots in your scatter plot. This is called a scatter plot, and every dot represents a score. So you can see on the left, I can draw a sausage shape or an oval and pretty well hit most of those scores. There's a relationship here. So the one on the left, there's actually a negative relationship. As the scores are, as the numbers across the x-axis are getting larger, they get smaller on the y-axis. Now look at the one on the right. If I try to draw any kind of oval to show a shape or a relationship, it's a nightmare. There's no way I can draw a nice, neat oval that shows a slope going through these scores. The right one actually has a correlation coefficient of negative 0.05. That is so close to zero. There's no relationship between the x and the y-axis in this case. So these would be the examples like how many servings of vegetables you eat and your employment satisfaction scale. There's going to be no relationship there between those. So this is one of those slides to mark or flag in your notes. Going across from the left to the right. The one on the left has an absolutely perfect positive correlation. All those dots line up so neatly along a little slope. It just looks like a ski slope there. And the slope is going up to the right. X-axis getting larger, Y-axis getting larger. The next one over, notice that the slope isn't as strong. It's a high positive correlation, but the dots aren't neatly along a line. It's going to take a little bit wider oval. And then as you move to the right, this is a low positive correlation of about 0.3. My oval, if I were to draw it around those, is getting wider and wider. The standard deviation of the scores from the mean is actually getting bigger, and they're spreading out from that line, from that slope. The middle one, there's no correlation. There, you cannot see a pattern there or a slope at all. Then the next one to the right, as the numbers across the x-axis are getting larger, the numbers along the y-axis, the scores, are actually getting smaller. So this is a low negative correlation. There's a slight slope going down to the right. The next one over, you can see that that's a high negative correlation. And then the furthest one to the right is an absolutely perfect negative correlation of -1. So I know exactly every time a number goes down 1 on the x-axis or goes up 1 on the x-axis, it's coming down 1 on the y-axis. So let's do a quick review. Descriptive statistics. We are measuring and telling stories and describing a sample data set. We're measuring the central tendency, which means we're talking about the mean, the median, and the mode. Mean is the average, mode is the most common, and median is the middle if I line them all up and rank them. I talked about variability and standard deviation. Remember, standard deviation is the average distance that score is from the mean, whether they're spread out very far and you get a large standard deviation, or they're very close together and you get a very small standard deviation. And then I described the normal distribution, or the normal curve, which is a frequency distribution. And most people, your more frequent scores are going to be in the middle. And if it's a perfect normal distribution, your mean and your median and your mode are going to be exactly the same in the middle. Then I talked about correlations, which are relationships. And you use a correlation coefficient to show the strength. It's going to be between 0 and 1. The higher shows the stronger relationship, the magnitude. And then the direction is going to be shown, whether the slope is going up to the right or down to the right. And that shows the direction of the correlation.